Good afternoon. This is Mihri Ozkan. I would like to talk about two ways towards decarbonization. First one is using the direct air capture of carbon dioxide technology. And the second one is electrification of mobility, mainly electrical vehicles. Before I start to my presentation, I would like to take this opportunity to thank the organizers for this invitation. And recently, I want to share with you the IPCC report by 2021. And the report says that the human influence on the climate and the global warming is real. And on the left, what you see here is the change in the global surface temperature observed since 1850. And since 1850, a fast increase in the global surface temperature has been observed. Today, this temperature value is reported as around like 1.27 centigrade. On the right, what we see is the natural events impact and the human impact combined, the contributions towards the global warming. And clearly we can notice that the human influence on the global warming is much higher as compared to the natural events. And this slide summarizes some of the scenarios that are studied. These are like 5 different changes in global surface temperature scenarios. And the last 2 is showing the high and very high greenhouse gas emissions and carbon dioxide emissions that roughly doubled from the current levels by the end of the century and then 2050. So these are 2 scenarios. And this 2 scenarios here also that showing these values as intermediate greenhouse emissions and the carbon dioxide emissions with the mid-century, and then the first one is also low and very low greenhouse gas emissions, and then carbon dioxide emissions. And we can see the impacts over here. As you can see, this is the highest level, and the highest level of carbon dioxide emission indeed results in the highest global surface temperature by around like much larger than the 4 degrees centigrade. And the expected scenario in the near term by 2040 is anywhere 1.6 degrees centigrade to 1.9 degrees centigrade. And by midterm is around like 2.4 or so. And this slide also summarizes the potential climatic impact and the drivers and their results. And we see more impact on the coastal regions, and they are mostly the flooding, erosion, and heat wave, and change in the acidity in the ocean. The same thing expected in the open ocean as well. Changes in the amount of heavy rain and flooding. At the same time, the drought is some other side effects to be expected. Right now, we are in the tipping point. We have to make a decision and then make the right moves for sustaining the life on Earth. The major challenge here is the population. The population increased about 6-fold right now and expected to be 9.2 billion by 2050. And will there be enough natural resources to support? And will there be habitable atmosphere to sustain the life? So these are the questions we need to answer. In addition, how can we support the well-being of people and the planet in areas where two intersect, and where we find the common and the best optimum conditions to keep both in a healthy situation. Impact of COVID-19 has been observed recently that last year the carbon dioxide emissions reduced from 2019, and this is around 6.4%. And this is not a permanent, it's temporary because of the blackouts and also stopping the aviation and transportation. But it does also indicate that, if it is desired, we can really control the emission of carbon dioxide. Negative emission technologies are there for us to do this. And if we look at the business as usual here, that the carbon dioxide emissions is increasing by mid-century, and also we can help to reduce this by using renewable energy sources such as solar, wind, and others. And we can remove additional carbon dioxide by using electrical vehicles, and electrification of the mobility is one solution. And using the negative emission technologies can bring us to net zero and even below. What are the technologies we can use? And these are coastal blue carbon, reforestation, forest management, agricultural practices, and bioenergy, carbon capture, direct air capture, and carbon mineralization are some of them. And based on the location, we can choose which one is most appropriate. And then based on the cost distribution, whichever one is more convenient and has low cost. And as we can see here, among all, the direct air capture has the highest cost. And I'm going to explain you soon what the reasons are. Let's look at first carbon emission from the industrial sources. And one of them is ammonia and corn ethanol plants. And this is about 80% of the carbon dioxide emission comes from their pipe. And if we try to capture that, it will cost us around $10 per ton. And from the steel plants or other chemical processes, this is around 15 to 80% carbon dioxide. And the cost to us is about $10 to $60 per ton. And also from the flue gas, coal, and natural gas fired power plants. And here the concentration is about 15%, and the cost to capture it is around $60 per ton. If we were to use direct air capture, so the pressure is much low, the pressure of carbon dioxide. It's around like 420 parts per million today. And that's why the cost is very high, around $200 to $600 per ton. So compared to the flue gas, we have to run around 2,500 times more air to capture the carbon dioxide. So that's the main reason why the DAC is more expensive. Recently, I published a commentary and talked about all the details of direct air capture. And this is one of the cartoons I prepared and also included in the publication. The industrial sectors such as cement and the biofuel or steel iron industry are hard to decarbonize. And there are distributed emissions from the aviation and transportation, and also many emissions recently from the wildfires that we need to offset. Additionally, about 8 billion tons of industrial carbon dioxide are coming from iron and steel and cement industries. And about 2 billion of the overall industrial carbon dioxide emissions each year cannot be avoided. And here, the direct air capture can really help to offset this carbon emission. So how that works, and if we need, the ambient air needs to be sucked in through fans, and then it's treated with a chemical sorbent, and later on it will be heated to extract the carbon dioxide, and then this carbon dioxide either sequestrated or used in other industries. There are two, operational DAC technology out there. One is the liquid, and the other one is the solid. And now I'm going to explain you the liquid capture process. And Carbon Engineering is the leading company with this technology. And the air basically goes in, and then it reacts with potassium hydroxide, and the product here is reacting with calcium hydroxide, and then you form calcium carbonate pellets, and at the same time forming pure carbon dioxide. All the chemicals are recycled and being used again. Carbon Engineering has operational plants, and at the same time under construction. The highest capacity is 1 million ton of carbon dioxide per year capture capacity, and it's under construction in Texas. The second one is the solid capture DAC, and here we have membranes that can absorb carbon dioxide. As the membranes are filled with carbon dioxide, this carbon dioxide is being released by heating to 100 degrees C, and it's been stored and then moved to location to be used. Climeworks is the leading company with this technology. They have about 14 pilot plants, and with the net capacity around like 2,000 tons per year. And they have another one in Zurich with the 900 capacity, and then under construction, which is in Iceland, about 4,000 tons per year capacity. This slide shows the locations of the operational and non-operational under construction and planning DAC plants, and mainly are in Europe, US, and Canada. Enabling technology is here is the carbon capture materials, and there are different classes based on their stages, some mature ones, next generation ones, and early stage ones. And each has their pros and cons, but overall, what we need is simply a good kinetics in the capture and then release of carbon dioxide, and selectivity to carbon dioxide, and also the stability so that they can go through many repeated cycles of capture, release, capture, release. We made a calculation in the group that looking at the Climeworks and the Carbon Engineering, the highest capacity plans, 4,000 for the case of Climeworks and 1 million for the Carbon Engineering, and running with the geothermal Climeworks, and then the Carbon Engineering running with natural gas. And for one DAC plant in the Climeworks case, we need 8,600 foot square. And this is about like 4 houses area. In the case of the Climeworks, this is about 200,000 meters square, and which is corresponding roughly 28 soccer fields. And if you were to remove the entire 1,000 ton of gigatons of carbon dioxide from the atmosphere by the end of the century, so we need 2.4 million Climeworks plant, or we need 9,980 plants of carbon engineering. They overall needs an area which is about 2.5 times New York City. The next important parameter is the cost, and the cost tells here two things. One is comparison of the capital cost versus the operating cost, and also the liquid sorbent versus the solid sorbent. And by comparing the capital cost of the liquid sorbent DAC versus the solid sorbent DAC, we see indeed that the solid sorbent capital cost is much higher. But in the case of the operational cost, and we see that the operational cost of the liquid sorbent is higher as compared to DAC, because it requires a higher temperature process around 800 degrees C versus 100 degrees C, and this is like more energy demanding process. And if you look at the amount of the energy demand for a solvent-based 1 million ton carbon dioxide per year, DAC system requires about 300 megawatt continuous power. And this is continuous because calciners cannot be cycled on and off. And this can be seen easily here that the liquid one, because high temperature process requires much higher energy demand and then versus lower demand in the solid case. And just making the comparisons in something we are much more familiar, and the liquid DAC corresponds to around 96 homes daily energy consumption versus the demand from the solid one is 63 homes daily energy consumption. And the source of the energy, where is it coming from, is also important. And this is the comparison: solar storage, nuclear, wind storage, natural gas, and geothermal. As you can see from the plot that the geothermal one is much less expensive as compared to the other ones, and about 42% less than the solar power generation. And if you were to remove 1,000 gigaton by 2100, we need about 13,000 DAC plants with the capacity of 1 million ton per carbon dioxide per year capacity. And that means that we need a capital investment of around 1.6 to 1.7 trillion. The point source capture is important. We should do that. But regardless, the point source capture also still lets 2 to 10% of the carbon dioxide through. So that's why we still need DAC to kind of like offset this. In US, Department of Energy increased its spending about 61% on carbon captures, and they allocated $240 million here directly to be used on new direct air capture R&D. Carbon engineering, the CEO recently mentioned that they are working on a third generation, and then they want to assure that the cost of the carbon capture can be lowered down to $100 per ton or less. And mechanical trees, it's another technology that came out of the Arizona State University. And they try to avoid and eliminate the cost of running fans and just using the wind directly to capture the carbon dioxide. And US tax code called for the 5Q offers tax credits for capturing carbon. And this is a great news. And even in California, there are more incentives created for carbon capturing. There is a huge interest from the oil companies to the direct air capture technology. And this plot just shows the top 20 companies that contributed around 480 billion tons of carbon dioxide since 1965. And the arrows showing some of them that already in contact and working together and invested into that technology. And the reason is they would like to get the carbon dioxide captured and use that to pump more oil to the surface. So this is kind of like a gray area, and this is something that we really need to pay attention. And second way of lowering the emissions is electrification of the mobility. In US, the transportation's contribution is 29%. By going electrical, and we can actually help to reduce this. This means that more EVs, and this means that we need more batteries. From today till 2030, the projection is that the increase in the demand will be about 14 times, and mainly for the electrical mobility than compared to energy storage or consumer electronics. And China is leading in battery manufacturing with 567 gigawatts, and the US and Europe are following that, and then the Japan and South Korea are also the key players in this. And Biden issued simply a rally, tried to encourage to have more EV gigafactories in Nevada, California, Tennessee, Michigan, and Georgia. So these are the gigafactories that are in production. And of course, making more battery means that we need more raw materials, and these raw materials are manganese, nickel, lithium, cobalt, and natural graphite. Whether we have sufficient amount of raw materials is a question. And then the China itself just providing larger than 65% of the graphite alone. So whether they will be able to meet the demand in increase in the EVs. So the supply, the recycling, and new battery technology development keep up with demand of growth. Will the adoption of electrical vehicles be hampered by the supply constraints, or can the cost of the raw materials and the cost of the batteries be controlled under this huge demand pressure? And are there any negative environmental impacts of overmining, fracking, producing large amount of raw materials for batteries? And then what we are going to do with all this large numbers of old batteries are some of the important questions to ask. In UC, I have this well-equipped lab that we are trying to address some of these questions that I raised earlier, and then I'm gonna go through over this. One of the questions we asked: can we use the plastic and glass waste to make batteries? And we know that about 80% of the plastics ends up in the landfills. Whether we can upgrade these and then we can use them. This movie shows indeed that we use the PET, water bottles, and we have taken pieces from them and dissolved them in a solution. And after that, in the movie, as you are going to watch, we created a cloth of this plastic and converted that into a carbon that we can use as an anode material, making supercapacitors and the batteries. At the end of the movie, what you are going to see is that one of those that we fabricated, we use it to turn on the LED light. And you see right here that the LED light is being turned on using one of our basically battery that is made of the PET. The second movie shows that we use a recycled glass bottle, and we crash that into small pieces, And after that, going through some chemical processes that gave us nanoporous silicon, and we turned that into, again, another battery, and then use it for powering, lights or other things. A biomass as part of a mushroom battery helped us to lower the overall cost by 15%. Another, sustainable source, which is sand, beet sand, is used to make more anodes, and then that lowered the cost around 30%. And glass waste, as you watched in the movie, also helped to lower the cost. And other renewable sources, diatoms and silicon paper and plastic wastes are used to make batteries. And with some of these batteries, we scaled up and then fabricated 15-layer batteries that actually gave us 33% better performance than Tesla and around 30% reduced cost. By elimination method, we try to make electrodes with the freestanding binderless and also without the aluminum foil. And so this simply helped us to reduce the weight about 6% and also lower the cost around 25%. Today, people are trying to increase the voltage, of course, in the batteries, and that's done by increasing the contents of nickel. But this has a cost, and there is a excess electrolyte oxidation and formation of the surface rock salt layers. And so this is indeed increasing the impedance. So that's something that people are heavily working on. On the anode side, adding silicon is definitely one trend to increase the capacity, but the first cycle irreversibility and the capacity loss are worked on, and large volume expansion or any kind of reduction and difficulty to achieving high enough Coulombic efficiency at the higher cycle numbers, like about 300 to 500, are still remain to be solved. So we need to learn how to control metastable materials, and we need to learn how to control interfacial structures, and we need to develop the realistic computational resources and some of the self-healing systems, such as some polymers, needs to be placed in action, and also need to develop new methods to increase our understanding of the multiple non-equilibrium processes in batteries. Humans are, if you look at this graph, are the tiny fraction of the weight of living things, and have, unfortunately, a disproportionately large impact on the environment. And the overall weight of all living things on Earth is around 550 gigatons. And the share of plants around 450 gigatons, and the share of bacteria is around 70, and the animals around 2 gigatons, and then the humans are 0.06 gigatons. But as I mentioned, even though this very less weight amount disproportionately have large impact on our environment, so we have a great responsibility to maintain and protect the earth, and maintain the weather and the climate, and make sure that it is sustainable for having life on Earth. So this is a big statement that we have to be really taking it seriously. With that, I would like to complete my presentation. And again, one more time, I would like to thank the organizers for this great opportunity. And at this point, application of negative emission technologies or carbon capture at the source or applying direct air capture is not an option at this point, based on all the experiences we have today, that wildfires and extreme weather, flooding, drought, and so on, we already see the impact, negative impact of global warming and carbon emissions. So this is now a must. And hopefully we can get all together and then trying to find the best way of moving forward. Thank you very much for the opportunity again, and I'll be happy to answer any questions you may have. Thank you.